हाँ, हंसो तुम, मजे करो, लो मजे। अच्छा जी, मैं ये रिपीट करने जा रहा हूँ क्योंकि ये पहले मैंने रिकॉर्डिंग वाला बटन नहीं प्रेस किया था। तो मैंने कहा है कि ये आपका ए है, ये बी है, बीच में, यानी कि ये थोड़ा सा ही एंड में रहता है, बाकी सारा तो हो गया था। ए की वैल्यू 8 थी एंड बी हैज द वैल्यू 6. We have also the C and D. Maybe C is 4 and D is C is 4 and D is also 0. So this whole is something 18 as a resultant value, 18. But according to a latest method, we have selected this one, the top one, top 50%. And after dividing 8 by 18 and 6 by 18, we have the value something I don't remember. Maybe what was the value? 0.4.
Sir, 0.4.
Okay, and 6 by 18, that was the value
0.3.
So these values are very much close to each other. And in elitist method, when you have these values very much close to each other, then you have to assign the equal proportionate to the selected members for your final selection. What I am saying that if you have to select 4 members and now your values are very much close to each other, these values 0.4 and 0.3, these values are very much close to each other. So, and these are 0.4 is for A and 0.3 is for B. So values are very much close to each other. We cannot distinguish the things easily. So what we can do now, we have to assign equal weight to both of these members. So 2 times A and 2 times B, because the value for A, which is 0.4, and the values for B, which is 0.3, it is not easy for me to differentiate that how much allocation I have to give to A and how much allocation I have to give to B. Or in other words, how much time I have to select A and how much time I have to select B. It is not easy for me to infer from these two very much close values. If these values are 0.25 and 0.75, then it is very easy for me to assign the proper proportionate. And now here I can do what? I can simply assign this. I can select B 3 times and I can select A 1 times according to these proportionate, according to these values. So this is in elitist method. After getting the top 50%, if you have, and after calculating the fitness value by using this method, 8 by 18, 6 by 18, you can also divide this 8 by 14, 6 by 14. What is this 14? 8 and 6, only 8 and 6. We are not considering this one. So this is also an option for you. So, but again, with 14, you will again see very much similar values. So from those values, you will not be able to infer again the distribution here. So in the latest method, after getting top 50%, you have to calculate the fitness like this one. And if you will get your values very much close to each other, then what you can do, you can simply select the members according to equal proportionate. It also depends, if you have further squares, then we can, for example, if suppose no, there is no suppose, leave it. I am coming back to my own philosophy. So, so what I am saying, because the things are going mess up and complicated and lengthy, so I don't want to go into very much detail. So that's why I just uh, leave those things there. Because when I will discuss that thing, then new questions will emerge, and we will uh, go in another direction, not on this topic. So that's why I just left the discussion there. So, so this is if after getting top 50%, if your values are very much close to each other, what you can do for your final selection, you can assign the equal proportionate here. For example, 2 times A and 2 times B, as you are seeing in your slides. But if your proportionate is very much clear, then you can assign, uh, for example, 0.25 is for A and 0.75 for B, and it is very much clear. I was saying at that time that it also depends on your number of spaces available here. When your spaces are larger as compared to these 4 spaces, then this proportionate has also some different meanings. So leave it. So leave it. Final conclusions, that if your values are very much close to each other and it is not easy to infer that how much proportionate I have to give, then you have to assign the same equal weightage to the members. And if the values are clear, then you have to assign according to the weightage. Uh, but in genetic algorithm, there is, you will select always 2 members, not 4. This is another question, another point. So you will not select 4 members. In genetic algorithm, you will select only 2 members. So this is something now going to be easy for you for your future. But this was in slides. I am going to stop my video and I am going to share the slide so that we can continue on. Now you are seeing the slides or not? आपको ये slides
सर
नजर आ रही हैं?
यस सर, नजर आ रही हैं सर.
Okay. So now this example was this example is with selection of 4 members, not 2. But in genetic algorithm, we will select 2 members, not 4. So this particular example is for 4 members, so maybe a little bit confusing, but I don't think so. It is confusing. Do you have any other question regarding this topic of roulette wheel and elite selection? Any students, if you have any question?
नो सर.
आप लोगों ने काफी तंग कर लिया, जाहिर बात अब नो ही कहना है. और बोलें, कोई क्वेश्चन हो? So this is the selection process, and with this selection process, what we will get these members. In genetic algorithm, these members would be 2, but here we have 4 members. And when we will select these members, then in step number 4, we will allow these members to propagate their genetic material to the next population. And now we will see that now we'll see that last step number 4. And that step is about the recombination of those members. As I said earlier, that in genetic algorithm, we will select 2 members, not 4 or 5 or anything else. We can select, but in normal tradition, we will select 2 members. and we will call those members the parents. And then we will apply the fourth step of the genetic algorithm, that is called the recombination process. And in recombination process, we have different operators. Those are called mutation, crossover, and what was the last one? Inversion. So we will apply those operations on those two members. Most of the time you will apply crossover, but there is a chance that you can apply the mutation and the inversion operation. But those mutation and inversion operation you will apply after calculating sub probability. So those two, mutation and inversion, is chance based, but crossover is the normal operation that you have to perform in genetic algorithm. This is mentioned here in this last point. So if mutation and inversion is a chance based, then it means you have to calculate the probability somewhere. So when you will get your members, when you will get your members selected after step number 3, then you maybe, if you are very much close to your solution, then this is the time that you have to calculate the probability, that you have to see the probability of the member. And if your probability is ranging from maybe 0.5 to 0.1, or maybe 0.85 to, oh sorry, 0.8 to 1, so something very much close to 1, if you have the probability like something very much close to 1, then this is the point that you can perform the mutation, or that you can perform the inversion operation. Otherwise, you have to apply the crossover operation. Okay, let's move on. And this is the slide which is just giving you the clarity about the different operators that we have. And these are, first, for example, this one is about the crossover, this is about the mutation, and this is about the inversion. So I can make my annotation tool active so that I can just highlight things here. Okay, so this is crossover operation, but on the left hand side you are seeing single point crossover. So I can make it a little bit bigger so that you can see this. Are you seeing the whole thing, the whole slide? Maybe the font is very much smaller and maybe you are not seeing anything. Is it okay? Are you
Yes,
seeing
sir.
all the things, or I have to make it a little bit bigger?
Yes, sir, it's okay.
That's good. I am looking at, if I have some option, then I can apply that option. Yes. Maybe now you have a little bit better view. So I am just making the annotation tool active. So here, this is single point crossover. In single point crossover, and in every operation, you have two parents and then you are creating two children. But in single point crossover, these parents are just like chromosomes, as John Holland was telling us in our previous slide, that these parents A and B are just like chromosomes. And in these chromosomes are potential solutions. What you have to do, you have to mark a point in the bit string of this parent, and that point would be the cut point. Actually, you have to cut these chromosomes here. And for example, here, if it is at the bit number maybe 8, then here you also have to highlight this point. So this is the cutting point. So now you can do what? You can replace this portion of parent B here in this portion of parent A, and then you will get child A as like this. And then you have to cut this portion of parent A, and then you have to swap this portion in parent B at this point, and you will get the child like this. So this is single point crossover. And in double point crossover, you again have the parents, but you have to mark 2 points, not 1 point. So maybe this is after 8th and this is the third last. So maybe this is the 8 and this is the same third last that we have. So the position would be same. Keep this thing in mind. If the position in parent A, that would be, you should have to keep that position same for parent B, because this is something you are going to change. And this is for in genetic algorithm, this is the string. This string can be of your DNA string or like that, or some genetic material. So you cannot alter this part with another part at different location. No, these points should be same in both the parents. So now you have to replace something, but between these 2 points. For example, here you can take this portion of parent B, and then you can replace it here in parent A, and then I am getting this child A. And similarly, I can take this portion of parent A and I can replace it in parent B, and I am getting this child B. So this is double point crossover, and now I'm sure that these concept of single point crossover and double point crossover are very much clear in your minds, because this is not something a complex thing. It's a very easy thing to understand. Is this so? So सबको समझ आ गई?
Yes, sir.
ये सब नहीं जवाब देते, सिर्फ एक ही बच्चा जवाब देता है. सो एनी हाउ, बाकी सारे लगता है सो रहे हैं. ये बस इन्होंने अपने कंप्यूटर्स को खाली ऑन किया हुआ है.
No, sir. सब जाग हम जाग.
अच्छा चलें. तो now this is the mutation, and here for mutation it is only allowed to change or replace one bit. It is not allowed to, you are not allowed to change more than one bit. So only single bit is allowed to be replaced. So for example, this is parent A and parent B. Running out of time. Okay. Just a minute. There is a message coming on the screen that I am running out of time. So I have to close this message. And I have to make this annotation tool again. So this is mutation. So parent A and parent B we have, and we are allowed to change only one bit. This is the rule. So mutation. So if this is the string of parent A, so I can change only one bit. So you are seeing that fourth last bit of this string is being changed, and we are getting child A. And similarly for parent B, now the position doesn't matter. Here the position matters. For example, the position marked for parent A would also be the same for parent B. Same concept here. But here for mutation, position doesn't matter. For parent A, okay, this is for parent A and you are getting an independent child. And this is for parent B and you are getting an independent child. So position doesn't matter. So you can change this bit at any position, but only one bit. But in inversion, you can change more than one bit. Bits, you can change more than one bits. But the condition or the rule is that you have to change those bits in one sequence. So it is not allowed to alter one bit at position 3, other at 5, other at 9. No, you have to alter the bits, or you can replace the bits quite more than one, but you should have to keep the order of the sequence. You have to keep the sequence in order. You cannot change one bit at position 2 and other one at 7 or 9. No, it is not allowed. So for example, here for parent B, you are changing the first 4 bits, and these bits are in a sequence, एक तरतीब में है, and then you are getting child B. So this is, again, these mutation and inversion are very much simple as compared to this crossover. यहाँ तक कोई क्वेश्चन है तो पूछ लें.
सर इन्वर्जन में सर
No,
अगर हम दो बिट छोड़ के हम चेंज करते रहें तो सर वो भी एक सीक्वेंस ही नहीं होगा सर.
और नई सीक्वेंस होगा, पता नहीं क्या सोचते रहते. जब मैंने कहा है कि वो एक ही सीक्वेंस हो, जब आप दो बिट छोड़ के करेंगे तो वो तो आप गलत कर रहे हैं. गैप तो आ रहा है ना बीच में. आपको एक ही दफा अलाउ है. यू आर अलाउड ओनली वंस फॉर इन्वर्जन. You are allowed only once. You can change the bits, for example, 3 or 4 or 5, but in a sequence. In a sequence. It is not allowed that you can change 2 bits here and then 2 bits here and 2 bits here. No, it is not allowed. Clear?
Okay, sir.
yes, sir.
Okay. Okay, then I have to. Okay, now again, this some theoretical discussion about genetic algorithm, and it is about the termination. Let's see. Maybe I have remaining 6 minutes in the ending of this section. Maybe, oh no, I have to come up again because I have to take attendance. So let's start. How this algorithm terminate? How will this algorithm terminate actually? This is the question now. Because in my previous discussion here, I said that I will get new members here and then I will update those members here in this population, and then I have to compute this process again. I will get again new members and then I have to update it here, those members, and then I will iterate again, and then I will get some new member again. So iteration will go in continuation. So then that's the reason that now we are putting this question, that when this algorithm will go into its termination state. So there are 2-3 different possibilities to terminate this algorithm. So one condition of termination is that when we will find our solution in our population, then we will allow the algorithm to terminate. And what would be that solution? For example, if I want to get a person in the population whose fitness value would be 80%, and if that person, if after iteration and iteration and iteration of genetic algorithm, if now if I am getting that person in my population with 80% fitness value, that is the member that I want, and that is my solution. So now this is the condition for me to get out of this algorithm, genetic algorithm. So this is something, an example, when you will have your solution in your population, then you can get out of this algorithm. The other criteria would be the designer criteria. A designer or the programmer of this genetic algorithm, maybe in future you will design this genetic algorithm, and after the end of this topic you will surely develop this you will surely do the exercise and you will surely design this genetic algorithm in some programming language, and then you will be allowed there. You will be the designer of your program. So then you can design your own criteria in your algorithm, that what would be the condition that after which you want that your algorithm would terminate. So the second possibility is that it would be the designer criteria, and that designer criteria can be hidden from the normal public or whatever. Like for example, Allah Almighty has the designer, the Allah Almighty is the designer of this universe, and He has the criteria that when this universe will end. Some of the symbols stated by our prophets, we know those symbols, but we as a Muslim don't know the detailed criteria of our designer when this universe will end. So Allah Almighty knows this better. So this is the second possibility, that the designer can build a criteria uh, for the termination of your algorithm, or you can let your population, or you can allow your population in the algorithm that they will do the process and they can end the algorithm by themselves. You can also do the things like that. And in the genetic algorithm of Allah Almighty, we are going in that direction. For example, humans are doing bad things, and we are basically allowing our universe to be ended soon. So anyhow, so we have some kind of वो क्या कहते हैं, इख्तियारात हमारे पास हैं. So anyhow, so this is the second option. So I am ending this session, and I am because this session is going to terminate in few seconds, and then I will introduce a new session, and I will explain this slide from that session. Okay.
Okay, sir.
Hmm.